So, hello everybody. Today we have the talk by Claudio Galicchio, and he's going to talk on deep learning for time series. He's an expert on the field. He's coming from the University of Pisa, computer science department. And please, we look forward to your talk.
Thank you. Thank you very much, Miguel, and thank you for inviting me for having this seminar, which is not about quantum computing. I'm afraid about that. It's about deep learning for time series with some stress on recurrent neural networks and reservoir computing, and a few of the, as I know that some of you, many of you probably are involved in the field of reservoir computing, could be probably of interest to see a few architectures that in Pisa we are developing. And let me start with a brief introduction. And this introduction starts by pointing out that time series and sequential data matter. And I think don't need to convince you, but you know, there are so many interesting applications that involve streams of data and temporal or sequential forms of data, like the Internet of Things, of course, automotive, human state monitoring. In all these cases, you have a lot of sensors, can be placed on the human, can be placed in the environment, can be placed on a machine, for example, and you want to make sense of all of these data. Or language, of course, like speech or even text, right? So nowadays, AI deep learning is all about text. Okay, and when we are in the field, let's say, of sequential data processing, the historical workhorse is basically recurrent neural networks, right? And here there is, let's say, a very simple representation of the vanilla recurrent neural networks, where you have two layers, basically. Apart from the input layer, you have a recurrent layer that is dynamical, and an output layer or readout layer that is statical and computes the output. So the recurrent layer computes a state transition function. I'm going to fix a little bit the notation, where h of t is the state computed at time step t. And this is a nonlinear function, where the nonlinearity is this phi here, of the input in the current time step and the state in the previous time step. Similarly, O of t is the output at time step t. That is a linear combination. For example, typically you have linear output layers, a linear combination of the state from the same time step. Okay, so this is very straightforward. The point is that all of these transformations are modulated by these weight matrices and biases. That includes parameters that need to be fixed and adapted based on the training problem, no, that you want to solve. And when you want to apply learning algorithms to all of these guys here, all the guys in green, you need to apply backpropagation through time, which is an extension of conventional backpropagation for time series processing. And this comes at a cost, right? Comes at a cost of compute, of energy, of time, and of course of money, right? Because you have to pay for the energy. All right, so the point is that training this kind of vanilla recurrent neural networks is difficult, and this was pointed out very clearly and interestingly in this famous paper by Pascano and collaborators in 2013, where they studied the dynamics of learning in recurrent neural networks. So this is a very nice read. So let's dive a little bit into this aspect. So why training recurrent neural networks is difficult? You know, training deep neural networks is difficult, basically. So what happens when I have my very simple vanilla recurrent neural network that I showed you previously, and I apply it to a problem, right? To an input temporal data, right? An input stream. I have what is called the unfolded architecture over time, which means that the same architecture is replicated for every time step, right? So time step 1, I gave the input x1, calculated the state h1 and the output o1. And then in time step 2, I calculated the state based on the new input and the previous state and so on and so forth, right? Until the last time step. And remember that all of these transformations, right, are the state transition functions that we have seen previously, repeated over time many times. So when we unfold vanilla recurrent neural network architecture over time, we have a very deep neural network architecture. And the depth is essentially the number of time steps that you have in your time series, right? So it can be very, 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 very deep. And the fact that this is a very deep calculation can imply and typically implies the same problems that you can have in very deep neural networks for training. And essentially, this means that the information needs to flow inside of this unfolded architecture, needs to flow well in forward and in backward ways. For example, in the forward phase, so when I calculate the output given the input, I can have potential instabilities due to the fact that, for example, the influence of some inputs can be vanishing progressively over time, right? Because maybe these transformations here in green are squashing too much the information, right? At the same time, the influence of this information here can, let's say, explode over time, right? So you can see this like a dynamical system. You need to avoid instabilities in the forward phase, correct? So you typically want to avoid instabilities, which means that a tiny perturbation in an input very far in the past determines a representation after a lot of time steps, not 5, but a lot of time steps, that is completely different, right? And so that the output from that can be, like in a sense, affected by the fact that I have destroyed my memory. Right? So you have these two problems. You can forget information, or you can destroy your memory because of the instability of this processing of the information in the forward phase. Similarly, when you consider training these kind of networks, you can have instabilities also in the backward propagation of the gradient. What does it mean? It means that at certain point when you have calculated the output, for example here, you will have an error or a loss value that you will use to calculate the gradients and modify weights here, right? And in all of the time steps. So basically here you can see that in practice, using backpropagation through time, you have to propagate back the gradients across the same architecture, but in the other direction. And so you have basically the same problem, but in the other direction. The gradients can vanish or can explode because of the instabilities of this process in the backward direction, okay? If the gradient explodes, so it means that your weight vectors or your weight matrices will explode, okay? So they will contain no useful information. If the gradients vanish, the point is that the training of this architecture becomes less effective on long-range propagation. What does it mean? It means that maybe when I gave this input to my network, the output at this time step is important that remembers what was in input here, right? And the same way, the way in which this input influences the state after a lot of time steps is important, okay? So when you want to, in a sense, when you vanish your gradients in this pathway from the output, let's say at this time step to the input, it means that you will not change these parameters in an effective way in order to change the output in a dependent fashion from this input, okay? So this is the basic point. And historically, this problem of vanishing, in particular vanishing gradients, led the community to move from simple vanilla recurrent neural network architectures like the one that I have discussed so far here on the left to more complicated, let's say, systems like long short-term memory networks or gated recurrent units, where you have, the basic idea is that you not only have a state h of t, like in the case of a vanilla recurrent neural network, but you also have another state information that is long-term information. And so you create another pathway for the computation in order to propagate effectively the gradients. So along this direction here, you can propagate effectively both the input and the gradients without at least potentially enabling the absence of this vanishing of gradients. Okay, so but what is the point now? The point is that okay, we have used long short-term memory networks for a long time, but the point is that they increase the number of computation that you need to do. Now you remember we had only one equation for the state transition function. Now we have 6, and we had only, let's say, this line before, like this line g of t. So we had 1, 2, and 3. Let's say guys with the trainable parameters. Now we have 3 times more trainable parameters, right? All of these in red. So what I mean is that if we can accept to train and to use better this kind of system, that we have to pay a cost and even, let's say, larger cost in terms of compute, memory, money, time, energy, etc., right? And maybe we don't want to really pay this price all the time, right? And maybe there are cases in which we do well even without all of this machinery, complicated stuff. And an example is given by embedded applications, right? Where you want your neural networks and your complicated, let's say, RNN systems to run on very limited devices like a Raspberry Pi, for example, right? Or the phone or your watch. Where not only you want to do inference, but maybe you also want to do learning, right? No, not only inference can be done, but learning is more complicated. And so what we've seen in the years is this transition between this idea of vanilla recurrent neural networks, where all the weights are trained end-to-end by backpropagation, towards what is called reservoir computing and eco-state networks, where now the stress and the focus is on the dynamical system perspective of the recurrent layer that is called the reservoir layer. And yeah, the focus is on initializing well the parameters in green of this state transition function and then leave them untrained. So we eliminate completely the need for backpropagation through time. All the problems related to gradient vanishing or explosions is overcome immediately. And we can create very small learning systems, right, where the only trainable part becomes the readout layer and the output layer that can be trained very efficiently using even closed form solutions, let's say closed form solution with iterative solutions, even better. But the point is that these systems can now be as small as required to be distributed in the environment, right? And in the past, for example, we have done a lot of experiments and we have done several results where we have used these systems, for example, implemented on the very small sensor that you have seen with the antenna on the robot here, for example. So the robot is moving in this hospital environment near Pisa, and our system based on this reservoir computing was receiving information from the environment and localizing the robot like a secondary localization system on the fly. So this was only possible because we used these reservoir computing systems, right? So what is that characterizes really eco-state networks and reservoir computing? So what is the magic that makes them work even without learning the internal connections is what is called the eco-state property. The eco-state property, very, very, very long story short, means that when we focus on the state transition function, that is this equation here of the vanilla recurrent neural networks, if you want, then we can initialize everything randomly and focus on the values that we put on this recurrent weight matrix WH. So what we do, we control the magnitude, or let's say the length of the eigenvalues of this matrix. And in particular, we control the longest eigenvalue of this matrix, which is the spectral radius of this matrix. And if this quantity is smaller than 1, then we have some practical how can I say, a practical condition in which the system will be asymptotically stable, right? It's not a sufficient condition. it's what is called a necessary condition under specific situations. But in general, you can, let's say, control the spectral radius of this matrix as a hyperparameter, and then, let's say, generate the individual values, in a sense, randomly, provided that the spectral radius is under control. There are several ways of doing this. For example, you can generate a random matrix WH and then rescale the values by a constant such that the spectral radius is equal to the one that you want. Okay, so if the spectral radius is typically smaller than 1, and for example, the default value is around 0.9. Okay, but what does it mean? It means that in practice, I am initializing my state transition function to be asymptotically stable. And in a very simple way, this can be visualized by these plots. So in this case, I'm not considering an actual input to the system. So it's like input-free, autonomous way of seeing the dynamics of this guy here. Initialized in 3 different initial conditions, right? The red, the blue, or the green. So if this eco-state property is in place, it means that the system will converge after a transient, let's say, to a unique solution. In this case, it's the origin because I don't have any input. If the eco-state property is not in place, it means that depending on the initial condition, even if I give the same input to my system, the solutions will diverge to different positions in the state space. Right, and so depending on the fact that I have started my dynamics in the red, in the blue, or in the green one, stars, then I can, let's say, move to different solutions, right? This is not good. This is typically not good for generalization in learning because you won't separate, let's say, different conditions, but not so much, okay? So because if this is a perturbation of each other, then when suppose that you train your systems on this red one, and then if you have a blue data point that drives my dynamics in another complete different part of the state space, I will never be able to recall the same output as this one, or a similar output to that one. Okay. So this is more or less an intuitive view on the eco-state property. And eco-state networks are cool in applications, like I showed you very briefly previously, but there are problems. And these problems are related exactly on this eco-state property. When I am imposing the eco-state property, I am in practice imposing the fading memory property of the system. This is okay for a lot of tasks, but actually, what is the fading memory doing to my system is, in practice, accepting the fact that the information can vanish over time. So my system can be dissipative. And in practice, if I have, for example, a time series classification problem, where given an input time series, in the very final time step, I want to compute the class of my time series, right? So here, in the representation in the last time step, I want that all of my input time series is represented, right? If I have this fading memory property, eco-state property, then only the last part, only the suffix will be represented, not the entire time series, right? So for example, if this point here actually is important to discriminate between different time series, in this time series classification setup, and I have this fading memory property, it will be very difficult for my system to solve this problem, right? For my eco-state network to solve the problem. This is what is called nowadays in the deep learning community, long-range information propagation. And it's difficult with conventional eco-state networks exactly, and in general also with conventional recurrent neural networks, exactly because of this fading memory characterization. So in the literature, so in the last few years, we have investigated quite a lot this problem. And the idea was, the question that we posed ourselves was, how is it possible to create a system that is still reservoir computing, so still without learning of the internal connections, but without the fading memory, right? So that could be used for time series classification in a better way, right? So change a little bit what we call the architectural bias of the neural net, The architectural bias is what your network is more naturally suitable to do, okay? And ecostate networks and vanilla recurrent neural networks are more naturally suitable to do fading memory computation, okay? So if you want to do non-fading memory computation with an ecostate network, you need to engineering to do a lot of things, right? It's not straightforward. And so this is one of the works that we have done in the last couple of years with a colleague of mine, Andrea Ceni from the University of Pisa. And the first one is residual ecostate network. I would like to introduce two of these. This is the first one, or RES ESN, in which we introduce an orthogonal temporal skip connection in the picture. And so we have this beautiful creature here. So in the left, you see again the same organization as a vanilla recurrent neural network, but inside of the green box, the reservoir layer is a little bit more complicated, not a lot, but just a little bit. So the green part is the, let's say, the computational graph of a conventional ecostate network, right? The dissipative part. But what we have added is like linear orthogonal path that connects time step t, the state in time step t minus 1 to the state in time step t. Okay, so what is the purpose of this one is to preserve as much as possible the information that is coming from the past. Okay, and the green part instead will add to this integration over time also the information from the new input. Okay, so in practice, the equation is this one on top of this slide, where this green part is the reservoir of the conventional ecostate network-like system, and the blue part is the added part, so-called temporal residual connection, whose goal is to create a path for the long-range propagation of the input. So we have these two guys here. And in particular, the temporal residual part here is modulated by an orthogonal matrix O that can be randomly generated, okay? So this part is a conventional reservoir multiplied by coefficient beta. This part, let's say, is the temporal skip connection part, which is modulated by a random generated orthogonal matrix. Random, but can be also fixed, okay? It can be like the ring that we are sometimes used to. And this alpha here is a hyperparameter of the system that we call the proximity hyperparameter because it determines, as in a moment will be more clear, how close the dynamics of all of these equation here is close to the edge of stability. Okay, so by simply adding this part here, we are changing the architectural bias of the ecostate network. And how can we investigate this? We can investigate this by studying the Jacobian of the recurrent state transition function. Here, for simplicity, I consider the Jacobian of the bias-free autonomous system, which means no input and no bias, okay? Just for simplicity of the discussion. And if you calculate this Jacobian, then you see that you have two components, right? This alpha O plus beta WH, where WH is the recurrent weight matrix. And so when you analyze the position values of this Jacobian, you can see that this part here tells you that the eigenvalues are distributed over a circle of radius alpha. And this part can be considered like a perturbation to this position, right? And tells you that the maximum perturbation compared to this distribution is of this quantity. So beta times the norm of the recurrent weight matrix. And when you, so the overall meaning is that the eigenvalues of this system are distributed within a tube around the circle of radius alpha. To visualize this, we have this situation, right? So alpha determines how close you are to the circle of radius 1, which is, let's say, the edge of stability circle, right? So for example, here alpha equal to 0.5 means that I am alpha away from the edge of stability. Alpha equal to 1 means that I am exactly at the edge of stability, and the other hyperparameters determine in practice how thick is this tube around the edge of stability region. Okay. The second kind of model that I would like to discuss is the Euler state network, which is based on discretizing a stable and non-dissipative ODE. This is also work from this year. All of these works are from 2024. So basically, what do we do in this case? We start from the ODE equation, or the version of the state transition function. So my reservoir now is continuous time reservoir, right? And I do a very simple consideration. I want that the Jacobian of this system has imaginary eigenvalues, because I want critical dynamics, okay? Exactly critical dynamics. So how can I do this? For example, I can very simply impose that this recurrent weight matrix WH is antisymmetric or skew-symmetric. If this is the case, then this system here is a Jacobian with eigenvalues exactly on the imaginary axis. Okay, after I have done this, this constraint, I discretize the system by the forward Euler method, and I obtain this nice equation for a layer of a recurrent neural network. So this can replace the equation of the reservoir, for example. But the point is that now this recurrent weight matrix, okay, what here was indicated in this way, now is indicated in this way, which means that this matrix here will be WH minus WH transpose will be antisymmetric by construction. So no matter what are exactly the values that I put in this matrix WH, the overall quality of the dynamics will not be affected. The dynamics will be critical anyway. Okay, so I don't need to train the weights here to have this critical property. Okay, there are a few hyperparameters like the step size of integration and the diffusion for stability reasons. But the point is that, again, all of these matrices here and bias vector here can be left untrained after the initialization. Okay, so now I have a system that operates exactly at the edge of stability. Okay. With some, let's say, some slack given by the hyperparameters that I have indicated. But the overall bias of my architecture now is no longer towards dissipative fading memory dynamics, but is exactly non-dissipative dynamics. So if I want to model a system and so to solve a task where I need to have this non-dissipative property, then using these equations, I can do that, okay, even without that. Okay, and this again can be visualized in the reservoir state space. And in this plot, I just want to show you that this is the ecostate network with the ecostate property, same situations as before. And this happens when we apply the same operation to an Euler state network. So instead of converging to the same solution, so forgetting the initial conditions, I will preserve the knowledge of my initial condition in the state. So what happens, the state will start to rotate around the origin, still preserving the reciprocal distances between the orbits of the system. So what does it mean? It means that I will never forget the fact that I started in the blue star or in the red star or in the green star. And this is only a partial view on it, because if you see these green, blue, and red like input perturbations, right? But not noise, perturbations that you want to remember, right? At a certain point, you want to remember that I have received a perturbation that moved me in the red, in the blue, or in the green. Then in this way, it's impossible by construction, and in this way, it becomes super simple to do. Okay. No, this is not happening. And this is actually a crucial difference between the Euler and the residual ecostate networks, because the residual ecostate networks is still dissipative. Okay, again, you can do the same study of the Jacobian of the bias-free autonomous system. And now you can see that you have the identity times, let's say, 1 minus gamma epsilon, where these gamma and epsilon are the hyperparameters, plus epsilon times the antisymmetric metrics, right? So this tells me in practice that the real part of my eigenvalues of the Jacobian will be 1 minus gamma epsilon exactly. Right? And the right part tells me that I will have an imaginary perturbation of this form. Let's say epsilon times the eigenvalues of these metrics, which are imaginary by construction because they are antisymmetric. And so visualizing, this is what you have. You will have a focus of the eigenvalues around the point, let's say, 1 minus gamma epsilon, depending on the value of gamma and epsilon, but typically very small. It will be very close to 1, exactly 1, not the circle, but 1, and with some, let's say, perturbation on the vertical axis, on the imaginary axis. Okay, so how these guys perform in applications? Of course, much better than ecostat networks. We found that on applications requiring, in a sense, a form of non-linear short-term memory, residual ecostat networks provided very, very, very good performance. This is like conventional or less conventional forms of memorization tasks, like memory capacity or memory capacity modulated by signs or some other forms. And these are the usual suspects that are used in reservoir computing, NARMA, Mekki-Glass, Lorentz, etc. So residual ecostat networks and variants that we have analyzed in a few papers give the striking best performances in these cases, right? Compared to conventional, let's say, leaky ESN or variants of that. Even compared to Euler-Stat networks, which actually performs very bad. So Euler-Stat networks perform very bad on problems involving short-term memorization. But what happens when we go to time series classification, then the story completely changes and reverses. Residual ecostat networks, okay, what you see here are a number of time series classification problems. Some of them are more complicated than others. Some of them are, let's say, short, others are quite long, like the sequential MNIST or the sequential F-MNIST. Sequential meaning that you have the image, and you consider like a pixel by pixel version of that image. So it gives like a very long one-dimensional time series. At the end of the time series, you want to classify based on what was in the image. So kind of complicated for a time series, for a sequential model. No? You have to remember more or less every part of your input time series. And in the different columns here, we have ecostat networks, not conventional ecostat network or leaky ecostat networks, actually. This is, let's say, a version of the ecostat network where the classification is not based only on the last time step, but on the average of all the time steps, okay? Trying to reduce the fading memory in this way, right? And this already, if you look at these results, they tell you that time series classification is difficult for a conventional ecostat network because this column improves almost everywhere, almost in any case, right? So for example, in this case, shape sol, you go from 60% to 71% of accuracy. These are accuracies. Okay, but when we go to the added models, what we can see that in general, the non-dissipative approaches, they can, here I've also indicated the average gain compared to ecostat networks. They can give you a substantial improvement compared to conventional systems, and especially the Euler-Stat network. The Euler-Stat network, almost 50%, like more than 40% of improvement compared to a conventional ecostat network system, right? So brings, let's say, reservoir computing to a new arena, in a sense, no? For the deep learning. And so this gave us the idea that probably we can avoid limiting ecostate networks and reservoir computing in general to be left to you guys, right? So we can try to probably use them too, right, in the deep learning community with success, right? But in order to do that, we probably need to resurrect reservoir computing, no, for this deep learning era. So how can we do resurrect reservoir computing for the deep learning era? We have a couple of strategies in mind in our group, but I would like to take a step back now for a few minutes and see what's happening now in the deep learning community, right? So you may be aware of the presence of this big monster here in the deep learning community. It's called the transformer, right? And you use it all the time where basically you use a version where you use only this part of the transformer all the time when you use ChatGPT, for example, right? There would be a lot of things to say about transformers, but first of all, that this is not a sequential model, right? This is a model that operates on sets of data. And indeed, in order for this to work on time series data, you need these two bolts here, the positional encoding. Otherwise, you will never be able to, let's say, discriminate information based on the time. But anyway, the point is that here we are using, in the case of a transformer, we're using only feed-forward operations, non-dynamical operations. And everything is based on this concept of the attention, multi-head attention, but basically self-attention, which means that I want to know how every token in my sentence can be correlated to all the other tokens in my sentence, right? So this is the core idea of the self-attention, which, by the way, was invented for recurrent neural networks, not for transformers. That was another story. The point is that you can use this very ugly thing in applications, and we actually do that at the time. But computationally, this is really not very good, right? So computationally, okay, the good point is that being only forward operations, you can parallelize on GPUs. This is a huge improvement compared to recurrent neural networks. Recurrent neural networks cannot be parallelizable, right, in GPUs, because there is this temporal constraint. You need to compute the state for time step t, then the state for time step t plus 1, etc., right? Here you compute everything together, right? All your time series can go together. But anyway, the point is that when you actually want to use this, you pay a cost in time that is quadratical with respect to the length of the sequence. Not only in training, but crucially also in inference. Okay, so if you want to do an inference on a very long sequence, every time you have to pay this cost. So this is bad, of course. Compared to these recurrent neural networks in operation, so in inference, they scale linearly with the length of the time series. Okay, so recurrent neural networks are are in a position of clear advantage compared to transformers for inference, right? But for training, recurrent neural networks cannot be parallelizable. So this is very tricky. And so what's happening? A few years ago, the community starts investigating if it was possible to change a little bit the way in which the transformers were created, and maybe to challenge the community to create lighter version of transformers that could be more efficient, so to avoid this quadratic cost in the inference. And so this paper appeared, Long Range Arena, a benchmark for efficient transformers. So because transformers scale badly, they created a pool of benchmark datasets. And this pool of benchmark datasets was supposed to challenge, let's say, all of the available versions of transformers, right? So the tasks were tasks of different types, but for example, one interesting one is this one, which is called Pathfinder, where you give these images to your network a pixel at a time, okay? Again, similar to a sequential lemnis, a pixel at a time. And you have to classify if the two dots that are present in the images are connected by a line or not. Okay, so in this case, for example, is yes, so positive. In this case, they are not connected, so negative. Okay, so what they found out, what they found was that actually it was very hard to find a system that is more efficient but better than transformers in the pool of these long-range arena tasks. Okay, so you can see here the speed against the score in these long-range arena tasks. Okay, so you can have higher speed, but the score is always almost lower than the one of transformers. And then a kind of a very old revolution appeared again, which is the state space models one. Okay, so what is a state space model? Probably all of you know. It's like a simplified way, a simplified class of recurrent layers where you remove the intermediate nonlinearity. Okay, so you have a linear recurrent layer in a sense. Okay. And now what is the point, the good point here, is that you can see this very simple set of equations from the continuous time perspective like an ODE. So you can put constraints, you can do a lot of tricks here, right? But then you can also discretize, and you can see this like a recurrent neural network, okay? But as this is linear, you can also see like a convolutional neural network, okay? So the idea is that you start from here, and depending on what you want to do, you can use one or the other of these three formulations. Like, for example, for training, you use convolutional formulation. For inference, you can use recurrent formulation. So you can get the best of the two worlds, right? Okay, these are some details, but the point is that this matrix A cannot be any random matrix. This is crucial. It should be a structured matrix, right? One example is this Hippo matrix here, which is based on the idea of projecting the information in the space of the Legendre polynomials where you have optimal memory. And then you can create a discrete time version for the inference. But for the training, like I said, you can create an equivalent, very big kernel of kernel ASO, we could say, of the equivalent, let's say, calculations. And very interestingly, what is here is that you have to calculate the powers of this discretized A matrix. And when you want to calculate these ones, you want to calculate these ones in an efficient way. So the matrix A should have some structure, but also should be, in a sense, diagonalizable. If it is diagonalizable, all of these can run in parallel very efficiently, scales in a very well fashion, and beat all of the transformers. So this is really neat, I think. So state space models, okay, of course, not simply in the, let's say, very vanilla formulation that I showed you, but you have like state space layer on top of another state space layer, on top of another state space layer. In between, you have nonlinearities like a multi-layer perceptron, okay? But the recurrence is linear, so can be trained in parallel in GPUs, okay? And like I said, this is the pool of long-range arena tasks. This last line is the, let's say, workhorse of state space model S4 and beats all of the transformers. And in particular, on a very complicated version of the Pathfinder where you have very big images, all of the transformers could not effectively propagate the information in a proper way, so they achieved 50% every time. This one reaches almost perfect classification. Okay, so how can we, what we're trying to do is like leveraging these ideas, but from the reservoir computing perspective, right? So this is the first thing that we came out with, is called the reservoir memory network that we have presented in a few venues right now. The basic idea here is that we want to have a modular we want to have a modular organization, right? So we have seen from the state space models theory and applications that memory is essentially a linear problem. So memory can be solved and should be solved by a linear system, okay? And in between, you can have nonlinearities, or as a readout, you can have a nonlinearity. This is fine. But the memorization part should be linear, right? So we came out with this organization with a dual reservoir, where we have a linear memory cell in orange here, and a nonlinear reservoir in green, okay? So the linear memory cell is fed by both the input and the state of the memory cell in the previous time step. Okay, here, similarly to the state space models, this recurrent matrix, VM, as I called it, is the equivalent of the matrix A for the state space models, should be structured, right? To give, let's say, potentially the longer, shorter memory that you can, right? So one possibility would be to use hypomatrices, like the one that I showed you before. We have used that, compare the results. Nothing better than what I'm telling you now. It's a simple ring, okay? So what we used here is the Peter Tigno's old proposal of using like a cycle reservoir, okay? So it means that this matrix has all zeros except the subdiagonal and on top right element, which is equal to 1. All of these elements have the largest spectral radius that you can imagine. Okay. And then on top of the linear reservoir memory cell, we have a nonlinear reservoir that is fed by both the external input, okay, by separate pathway, and the output of the linear reservoir cell. Okay, so this can be, for example, a leaky ecostat network, but augmented also with the input coming from the memory state. Or why not? Can be an Euler state network, right? Again, augmented by the memory state. We've done a lot of analysis on these tasks, but I would like to mention at least one result in the little time that I have left. That is the results that we had on pixel by pixel permuted sequential MNIST classification. So this is an even harder version of the sequential MNIST. So we take these MNIST images, we sequentialize like before, and then we scramble the positions. So now you really, even more, need to, your system is challenged to remember as far as possible in the past in order to do a proper classification of the digit that is represented in the image. All right, so what you can see here is on the vertical axis, the accuracy. On the horizontal axis, we scaled the reservoir systems and we counted the number of resulting trainable parameters. Trainable parameters are only the connections from the last reservoir, the green reservoir, to the output layer, only those. And we scale from a little model with like 1,000 trainable parameters to deep learning kind of, or deep learning-ish sized model of around 150 case parameters, right? So what we can see here is that the ecostat network is the gray line. The Euler state network is the orange line. There is some decrease in the end, some strange behavior. The reservoir memory network is in green. And when I use the Euler state network as the last layer of the reservoir memory network is in blue. So very big improvement compared to conventional reservoir computing and also compared to Euler state network. And for example, the performance that you can get with the reservoir memory network is more than 10% more accurate than what you can get with a conventional ecostat network. And if you look instead at the same level of performance, we match the best ESM performance with the reduction of trainable parameters right here by more than 96%, which is, I think, quite impressive. Also, compared to what else is there in the deep learning community, we compare quite well. Actually, we achieve like this 98.1 as the highest result, which is very close or even much better than some of the state-of-the-art models in deep learning for recurrent neural networks. So very competitive performance. All right. So do we really need extensive training in order to achieve performance on time series classification or in general on time series problems that is close to what you can achieve with state-of-the-art deep learning models? Probably we did, but based on what we are experiencing right now with our analysis, apparently, actually, we don't. Okay, we need to give away of the fading memory property somehow, as much as we can, and modularize our architecture in different parts. Okay, so for the future and current directions that we are pursuing, modular reservoirs. So if I have to solve memory, I use a linear system with a specific structure. Otherwise, I can use a nonlinear system. So no any meaning in using a nonlinear system for the memory, for example, right? Hybrid reservoir and trainable models. This is really strange that in general, out there, we never use reservoirs and trainable systems together. And of course, alternative to backpropagation learning. But the most important thing, I believe, is to scale the reservoir dimensions to huge sizes, right? So we have a couple of ideas on how to do that coming soon, hopefully. But I mean like having reservoirs like 1 million units in the reservoir, 1 billion units in the reservoir. Then you would see probably no difference in the results that you can have compared if the organization of the architecture is proper in the results that you can have with deep learning systems in the literature. Okay. This is it from me today. I thank you a lot for your attention. And this is it for now. Okay.
All right. Thank you, Claudio. So, James.
Thank you very much, Claudio, for the very nice talk.
Thank you.
If you just go to the, I mean, it's just more of a curiosity comment. If you go just to the last slide, I mean, to the previous slide, you're mentioning this goal of scale reservoir systems to huge dimensions. I don't have a question, but more a remark. I mean, recently I've seen, I mean, some of the top guys in AI, like Joshua Benjo, for instance, that you have mentioned, and so on. And they're saying that lately, I mean, people really training these huge dimensions, but not with scale, with reservoir systems, are finding a plateau. You have probably seen these reports of them. So you really think that reservoir systems can overcome this plateau problem? I mean, can really scale well?
No, no. No, I don't think so. But I think that the limit, at least in some parts of the architecture of the deep learning systems overall, that you can have when you create them using reservoir computers is in the dimension of the reservoir layers for the reservoir computing components. So, and yeah, I strongly believe that for memorization purposes, you don't need learning, right? So you can have a very complicated architecture, some modules for memory, other modules for other stuff. You can train the modules for other stuff, but don't do the learning in the modules for memory, right? So you can plug it in a reservoir system there, and you should put there the largest reservoir system that you can. This is what I mean. Probably you will not be able to scale better than trainable systems because, after all, in inference is the same, right? But compared to in the arena of reservoir computing, we need to use huge dimension. This is my message.
It seems that kind of a wall, I mean, it's been attained now. I mean, for example, this plateau is
Probably could be that this plateau is related to the data, or this plateau is related to the way in which the information is processed by the neural architectures. Maybe one of these two things should change in order to overcome the plateau. We'll see.
Thank you.
Welcome.
Thank you. Other questions? Comments? No? Let's thank Claudio again.
Thank you.